Welcome and thank you for joining. In this video, we'll look into graphs of polynomial functions. So far we have looked into the graph analysis, complete analysis of polynomial functions when we were given the equation of a function and then we had to draw the graph with all the specific features and all the important points. So in these examples, we are going to analyze polynomial functions qualitatively, which means that we are given features of the graph of a function and then we have to predict the shape of it and possibly create an equation that fits the description. So we'll start with example number 1 where we're told that f of x, the function we're trying to draw and predict the graph of, is increasing for x values less than -2 and for x values greater than 3. It has only one point of inflection and f of x is positive in the interval from -4 to 0 and for x values greater than 6. So we have to draw the graph and write a possible equation in factored form. So as I mentioned in class, whenever we solve a problem, any type of problem in math, we first want to read the problem to get an idea what it is about and then read it a second time and read it with purpose and try to understand what information is important and what is not important. And if there are specific words or terms, try to recall the meaning of it. So what does it mean to have an inflection point, for example, at 0, 0, etc., etc. So whenever we draw graphs qualitatively, our focus must first be on where the function is positive and where the function is negative, because that can tell us for what x values the function will be above and for what x values will be below the x-axis. And not only that, but whenever a function changes its values from positive to negative, it means that it has to pass through zeros. And vice versa, if a function is going from positive to negative, and from negative to positive, the function has to pass through the zeros. So the endpoints of the intervals where the function is positive will be the x-intercepts of the graph of a function. So in this case, we have the values of x equals -4, x equals 0, and x equals 6. So we're going to write in here that there will be an x-intercept at -4, an x-intercept at 0, and an x-intercept at 6. So all these questions are basically about translating or interpreting the information given in multiple ways so that we can gather as much information about the function as possible. So once you get the values, or the x-intercept, the values where the function increases or decreases, then I would try to plot them. And x-intercepts are very important in determining the shape of the graph of a function because they are like the foundations of it. This is where the function is sitting, right at the intercepts, right? So we have the x-intercepts. Oops, I made a typo here. 6 I meant. And we have 1, 2, 3, 4, 5, 6, and I'm going to try to make them also a little bit more visible. So, and mark them by a red dot. So I know that the function will be positive between -4 and 0, so that means above the x-axis, and it will be positive for x values greater than 6. So right here. So next I will look into the rest of the information. So every piece of information here is important. So the function is increasing for x less than -2 and for x greater than 3. So I'm going to go at x equals -2. And if it helps, use highlighters to distinguish one piece of information from the other, because every piece of information given will shape the graph or will give information about different parts of the graph. All right. So at x equals -2, I'm going to plot it down here, and at x equals 3, right? So these are two important points. So for x less than -2, so for these x values, the function is increasing. So if we have a function, a polynomial function, where domain is any real number that passes through x equals -4, it means that if a function is increasing, then it has to go this way. and at x equals -2 somewhere has to make a turn. Now, if you're thinking, okay, so what other ways, what other ways can the function behave? So what are the other possibilities? So remember that polynomial functions are curves, right? They go up and down. And if a function is increasing, it means that when you are, for x values at -infinity, we have to start down here in order to go up. Because if you are in this quadrant, then the function will have to decrease. So I'm going to draw the graph with not a lot of confidence because I want to make this as accurate as possible. And always, pay attention to every piece of information here. And then it is also increasing for x bigger than 3, which means that up to x equals 3, probably the function is at a lower value and then it starts increasing. Now, I have a cue in here that can, or a clue that the x-intercept is right at this point and the function will be above the x-axis. So in a way, I kind of know that the graph of the function will have to pass here, but I don't know if it's going to go this way, or do I? Well, if it says that the function is positive, and this is the other end of the graph, it means that the only way for the graph to go would be this way. So I will draw this graph or this part, sketch this part with no hesitation. Now, at x equals +3, the function starts increasing, which means that if we have the graph in here, then it means that up to x equals 3, it's at some lower point, and then it starts going up. So I will draw the rest of the graph, try to make it nice and curvy, and we're almost at the end where we have to complete the graph. We have the two ends of it, all right, and we have the maximums at -2, it seems, and we have a minimum point at 3, and we know that the graph will pass through the point x equals 0. And I will draw the graph of the function that passes through this point, and I'm going to keep it nice and easy, nice and simple here. There goes the graph of this function. Now, in the next question, we're asked to write a possible equation and in factor form. Remember that when we are asked to find a possible equation, it means that there may be more than one equation that fit the description. And if you look at this graph, it seems like a third-degree polynomial function, and it is a third-degree polynomial function. But when you think about it, this is not the only shape that this kind of function can have. So another possibility would be to have, for example, an inflection point right here at x equals 0, right? And then make it down to the lowest point in here at x equals 3, okay? And that will make the equation, or what that will make x equals 0 a third root or a third factor in the polynomial function. So for now, I'm just going to leave the equation or the graph of this function as is. And I would say that with roots at x equals -4, 0, and +6, then the factors will be x plus 4, x, and x minus 6. And the equation of a polynomial function with indicated zeros will be any member of the family. That's why we have the letter A in there. And then x plus 4 times x minus 6. So that is one possible equation. Now, when you think about it, and I've mentioned that before, this is a first order 0. It appears to be a first order 0, and that's why x is to the power of 1, which makes this entire polynomial function a third degree polynomial. However, it can also happen that the x-intercept at 0 can be also an inflection point, which will make this a third degree 0. So another possible equation would be the same as we have before. F of x equals a, and then x plus 4, x to the power of 3, and then x minus 6. So when you look at this question, well, obviously we have answered both questions asked in here, but if you were asked to find or to determine what would be a possible sign of the coefficient a, then you would think that since this is an odd degree polynomial function, so this is a third, but even if we chose to give x the power of 3 and make this an inflection point, for example, that would be again an odd degree polynomial function. It would be a fifth degree polynomial. And you know what? I'm going to draw these graphs just in case anyone is confused about it. So another possible graph can be this. Right here. Okay, so the end behaviors are specifically described in here, so we know that there is no other way that we can actually direct the function at the ends. So, and that tells us that the leading coefficient of this odd degree polynomial function that extends from quadrant 3 to quadrant 1 has to be positive. So if that was a question on the test and it asks you what would be the leading coefficient of it, right, this is how you would explain it, right? So in the next question, we are given the function that has a local maximum at x equals 1, y equals 0. So this would be a point on the graph, but if you look at it more attentively and always look for points that have one of their coordinates equal to 0, they're not just ordinary points, so think where the y value of a point is 0. It's on the x-axis, which means that not only this is a local maximum, but this is also an x-intercept. So when you look at it a little bit more closely even, and I'm going to plot the point right here. So if a function has an x-intercept at 1, and also at this point the function marks a local maximum, it means that that must be a second order root, and the shape of the graph of the function should go this way. Okay, obviously it cannot go this way because that will make it a local minimum, whereas this one is a local maximum. So we're going to say that x-intercept is 1, which means that there will be a factor in the polynomial function of x minus 1, and not only that, but the factor will be of order 2. So look at how much we discover from reading into this little point, or this small little statement here. So a maximum at 1, 0 means that we got an x-intercept, which tells us what the factor is, and we know that the order must be 2. It extends from quadrant 2 to 4, so that means from quadrant 2 to quadrant 4 would be from here to here. Now, a function that extends across the origin means that it's an odd degree polynomial function. What else do you think would derive from here? So if the function goes from quadrant 2 to 4, not only is odd degree, but also we know that the leading coefficient will be negative because it behaves like the straight line or linear function that has a negative slope. Now it increases from -1 to 1. So whenever we are given that the function is increasing or decreasing in an interval, it means that it's increasing. It means that it's going to reach some high point, right? And somewhere in between. So, and it's going to hit some low point somewhere in between. So the increasing and decreasing intervals may give us min and maximum points, local min and maximum. I'm going to wait for this information here because my focus is the x-intercept. So one of the x-intercepts is at x equals -2. So that means that, as the problem says, x-intercept is -2 will be another point on the graph here. So here we go. We have the graph of a function that starts in quadrant 2, ends in quadrant 4. And it has an x-intercept at -2. And it's going to have to hit x equals 1. That's the next x-intercept. It should make a turn because it's a double zero and the graph should go this way around. So this is a general shape of the graph, but I also want to make sure that I have included this information, or I have reflected this quality of the graph on the gradient here. So it's increasing from -1 to 1. So x equals -1 is somewhere here. X equals 1 is right here. So I'm going to write that down so I remind myself of what's going on here. And now I can draw the graph with a lot more confidence and say that the graph will start in quadrant 2. It will hit the x-intercept at -2. It will decrease up to -1 because after -1 is making its way towards the next intercept, which is at 1 and increasing, and then it's going down. So again, this is not the only graph that we can draw given the features of the polynomial function, but let's create the equation of it first, and then we'll talk about other possibilities. So we're going to say that the function f of x will have a factor of x plus 2, another factor of x minus 1 to the power of 2, and we know for sure that the leading coefficient will be a negative number. Now, as I was mentioning before, we have other possibilities as well, and what we can build in here is a third order root at x equals -2, go down, go up again. So another possible equation in this case would be f of x equals negative x plus 2 to the power of 3, x minus 1 to the power of 2. What we know for sure though is that this will be an odd degree polynomial function. There goes another possible graph. And the leading coefficient of it will be negative. So if you have a question like this on the test, what you have to do is create only one graph, find only one equation. We don't have to explore them all, but what is important is to read the information carefully and closely and try to derive as much information from every single statement as possible and put them on the graph in order. Start with the x-intercepts, continue with the end behaviors, and then the increasing and decreasing intervals. So in the next video, I will go over some other examples where different sets of features of a polynomial function are given. Bye for now, and thank you for learning with me.